In this video we're going to look at the vertical spring. We will suspend a mass from a vertical spring and look at its properties. So there's our spring without any mass attached to it, and we have some equilibrium position, and if we attach a mass we now have a new equilibrium position. If we put a different mass we would have a different equilibrium position again. So let's just look at the second one. This now becomes our new equilibrium position, and we'll find that if we set this spring in oscillation, it will oscillate around that equilibrium position, just as the other mass would also oscillate around the new equilibrium position. So what we want to look at is how the spring properties depend on this equilibrium position. So we start off with a spring which doesn't have a match to it, a mass attached to it, and we attach a mass and we let that mass come to equilibrium so that the forces balance. Right, and at that position x is equal to x naught. So we'll define our coordinate system so that plus y is upwards. Right, so plus y is upwards, and we have two forces in this system. We have the upwards force of the spring, which is equal to k times x naught, and we have the weight of the spring, which is equal to minus mg. The system is in equilibrium, so the sum of all the forces are equal to 0. The weight plus the spring force is equal to 0. The weight is minus mg, and the spring force is plus kx0. Right, that's from Hooke's law. You should keep this result in your mind for when we get to the next section. So here is the situation we have. We've got our original spring, x is equal to 0. We've let this attach to mass and it's come to equilibrium, x is equal to minus x0. And now we've stretched the spring some distance a. Actually, we can stretch it anywhere between an extra from 0 to a. And in this case, what we have is, again, the sum of the forces are equal to the weight plus the spring force. The weight's minus mg, and the spring force is k x naught plus x. So we've got a component of the spring force which is equal to the original one, kx naught, and we've got one equal to the extra displacement, kx. Now, since we found in the previous part that minus mg plus kx naught is equal to naught, we get from the above equation that the sum of all forces is just equal to kx, which is what we started with. So the properties of this spring are just defined by an equation that looks exactly the same as we started off with. The sum of all the forces on the spring when it's been moved from equilibrium is equal to k times x. The net force on the mass does not depend on the weight, and therefore any subsequent motion of the object which is attached to the spring doesn't depend on the gravitational force.